go ahead and record. Any questions before we get started? Okay, so we're on method of steepest descents. Again, this is sometimes called the saddle point method because to leading order, you're looking for a saddle in the complex plane that you can expand around, and you know, so in one direction it serves as a maximum, so it's analogous in that sense to Laplace's method. We're looking for asymptotics for contour integrals like this. Let's say for large x, rho of t is complex, and c is contour in the complex plane. Okay, and then we call f of t the amplitude. Okay, and so we remarked that we're going to use some concepts from complex integration in order to solve this, some complex analysis concepts for analytic functions. And we had started by working through an example. In particular was to evaluate I of x equals the integral from minus infinity to infinity of cosine kx divided by x plus b squared plus a squared dx, right? So this contour is along the real axis, okay? K is greater than 0, A is greater than 0, B is in R. But as you might remember, we created a contour in the complex plane in order to try and solve this. And the idea is that Cauchy's theorem allows us to compute a contour integral based on the poles that we find for a function that's encompassed by some contour. And so we rewrote this as a Fourier integral for starters. And so we said I is equal to the real part of I plus real part of integral from minus infinity to infinity e to the I kx divided by x plus b quantity squared plus a squared dx, okay? And then we introduced a simple closed contour now that lives in the complex plane. And so we have a half circle whose radius is going to grow towards infinity. But for a fixed r, we can write down the integral. So we'll call this part of it CR, that's going to be the arc of it. Real part of, not B, I will use X here. Okay. And so this has radius R here. And we have a pole for our function that lives inside of this contour as long as we make R large enough, okay? So the only singularity of our integrand inside our contour, so this is our little simple closed contour C, is some point we'll call Z0, which is I A minus B, okay? So then we can take the closed contour integral, and by the residue theorem, we get that this is equal to the residue of f evaluated at z0 times 2 pi I, or in other words, it's equal to, so yeah, so before we compute this, let me show the intermediate steps, okay? So what's f of z here? F of z is going to be equal to e to the I k z divided by z plus b squared plus a squared, right? Our residue is going to be the coefficient of 1 over z minus z0 that we could get by partial fractions, okay? And the expansion near z0, okay? And so in order to figure out what this is, we just need to factor out this quadratic here, okay? So let's do that. Can I flip the page? Everybody done writing? Okay. So f of z is equal to e to the I k z divided by z minus I a b z plus I a plus b, which is approximately leading order e to the I k z0 right around the pole, z minus z0 z minus z conjugate. Zero. So e the I k z0 divided by 2ia times 1 over z minus z0. Okay. So right around the pole. Okay. So the contribution around the pole then is just going to be whatever our the non 1 over z minus z0 part is when we're right around that pole, approximately around that pole to leading order. That's going to give us our residue according to the residue theorem, which just says take the product of z minus z0 and f of z and take the limit as z goes to z0, okay? And you would cancel out this term and you would just get the rest of your function that remains evaluated at the singularity, okay? So our residue then gives us the following formula for that contour integral, okay? All right. And so, right, okay. So then in the limit, as r goes to infinity, this contour integral is going to be equal to I plus the limit as r goes to infinity, the integral along the contour CR. Remember, that's that arc that has radius r. But this essentially is going to be through the same arguments that we worked out before, vanishing to 0. So if you remember several lectures ago, we took the integral of e to the I z squared along an arc, and we showed that in the limit as that arc's radius goes to infinity, it's going to vanish, okay? So this term is going to vanish here. And I'll just write C integral for e to the I z squared that we computed a few lectures ago. And so that means that this integral I plus is just going to be pi over a e to the minus I k a e to the minus I b k. Okay. And then we just get from the residue theorem of this contour integral. So the real part of I plus is going to be pi over a, e to the minus ka, cosine dk, which is equal to our integral I. All right. Now, this example, right? We were able to essentially just take a contour integral and do this. We didn't necessarily have to find a specific saddle point. However, we found that the dominant term in our integral was that singularity, that pole that lived inside the contour that we created. Okay, so this maybe gives us some clue as to what we're looking for in steepest descent. Typically, the dominant terms may be associated with poles. So let's talk a little bit more about how to motivate our steepest descent approach. Okay. So in general, we're going to ask what vectors are orthogonal to the level curve of our integrand f of xy equals f of x0, y0. Okay. And so the idea is that if we have some function here, okay, if we take the gradient of that at some point, x0, y0, that's going to give us our steepest ascent and descent directions for, let's say, the function f equals f of x0, y0, okay? So any scaling of gradient of f of x0, y0 for some non-zero scalar is going to be these perpendicular vectors, okay, to our level curve at that particular point, okay? Now, on some surface, right, z is equal to f of x, y. What is what's called the steepest descent direction? Well, again, it's going to be probably related to gradients, right? And in particular, right, if I take minus gradient of f divided by the magnitude of gradient of f, just to normalize, this would be our steepest descent direction. And by that same token, the gradient of f divided by its magnitude is going to be our steepest ascent direction, okay, from vector calculus. So how does this tell us something about integrals or integrands of steepest descent problems? Well, let's look back at our contour integral that is sort of the general focus of our steepest descent method, okay? So steepest descent for the integral I of x, integral over c, h of t, e to the x rho of t dt as x goes to infinity, okay? The overview is that we're going to use Cauchy's theorem to deform whatever our contour is to C prime, okay, where H rho are still analytic along that contour, okay, such that the imaginary part of rho of t is going to be constant, okay, for t along C prime, okay? So the idea is that somehow we find some part, some contour that we can draw in the complex plane such that this argument, right, up here of our exponential is going to be constant, right? And so this should feel a little bit like stationary phase or maybe like Laplace's method, right? Because we're trying to find some region where we have a flat part of our function that's going to create a large contribution because it's not changing very much, even though it has this prefactor that's very large, okay?
What is the word before analytic in parentheses there?
Oh yeah, so H and rho are analytic.
Oh, okay.
Yeah, sorry. Okay. So then what we'll do is we're going to apply Laplace's method for the real exponential integral, okay? And the generically dominant contribution, okay, will be from points where rho prime T0 is equal to 0, okay? Now, remember, this is a complex function, right? So you have a real part and you also have an imaginary part. And this is what steepest descent sort of handles in this case, is it sort of handles a maximum in the real part and almost like a stationary phase component in the imaginary part, okay? So our geometric explanation is that if we let rho of t equal rho of u plus iv equal some phi of uv plus I psi uv, okay? The idea is to seek this contour C prime that is a level curve of psi of uv equals psi of u0 v0, okay? The gradient in uv of psi should be perpendicular to C prime. And what does this bias? We'll see. The gradient of rho, which is equal to, sorry, not rho, but phi sub u, phi sub v, right? Because we have an analytic function, should be equal to psi v minus psi u, right? So this is just by the Cauchy-Riemann equations for analytic functions, which we take them to be. And so what does this imply? It implies that gradient of phi, gradient of psi, dotted, is equal to 0. This implies that gradient of phi is going to be tangent to C prime, our contour that we've constructed. So then what does this mean? Well, what it means is that gradient of phi is the steepest ascent direction on the surface. Real part of rho is equal to phi of uv. Moreover, minus gradient of rho is the steepest descent direction, okay? And so we want to follow this direction, okay? Because as we're falling off in the steepest descent direction, okay, that's going to provide us with the best approximation, okay? So imagine if you just have some quadratic function, okay? The more steeply it falls off, okay, then the better approximation, then the sort of less of a contribution, I guess, you'll have to the integral, right? From the sort of flanking regions around the point that you're focusing on. The more rapidly your integrand falls off, right, the more that sort of point mass there is representative of the integral, okay? So if you find the steepest descent direction, that gives you sort of the best approximation in that case, okay? So suppose that the derivative of rho evaluated at t0 equals 0, right? This implies then that these functions that we constructed have gradient at t0 given by 0, okay? Okay, so this means that we have.
One of those be a psi.
Sorry. Oh yeah. So that means that t0 is going to be a critical point for the surfaces. Rho equals rho. Phi equals phi uv, and psi equals psi uv. Okay. Moreover, rho and psi are harmonic functions by the Cauchy-Riemann equations. Okay. So by the Max principle, rho does not attain a max or min at t0, okay? It's a critical point on a surface, okay? But because it's a harmonic function, okay, it can't obtain a max, okay, by the Max principle. So that means at t0, the only thing it could be is a saddle point, okay? This is one of the reasons why this is called a saddle point method. So if we draw this curve, rho of uv, I have u and v here, and I draw the surface, right? Then somewhere living in here, let's say, is my t0, which is going to be a saddle point, u0 plus iv0 right here, okay? this is the point that I want to identify, right? So rather than identifying a max or stationary phase point, right, we're looking both in the real and the complex directions, okay? And we want to find the particular point that has these surfaces increasing in one direction and sort of falling off in another direction, okay? So C prime is going to be the point where psi equals psi of u0, v0, and rho, phi of uv is a max at u0, v0, but only if we look along C prime, okay? So our comment then is that if d rho dt of t0 is not equal to 0, then phi is not a max at u0, v0, because the gradient of rho of phi at t equals t0 is not equal to 0 in that case. Okay. So what does this buy us? Okay. We have this deformation process now. We've selected a deformed contour, okay, that maybe doesn't necessarily, it won't in general look like your original contour, but the idea is that you are going to draw a closed contour that's going to connect back to this contour C prime. That closed contour will allow you to compute a closed contour integral using Cauchy's theorem, okay? And in particular, the way that you're going to draw that contour is along a very special direction and through a very special point, which is going to be a saddle point of these functions, so that you get rapid fall off in one direction and you get an increase of your surface in another direction, okay? I'm almost to the punchline here, okay? The idea now is that I of x is going to equal Ix, the imaginary part of rho t, is actually rho t, C prime h of t e to the x real part of rho t dt, okay? This is going to be our contribution from the deformation process. And the main takeaway here is that the steepest descent paths are going to be curves with constant imaginary part, okay? So our local analysis then of the saddle point is going to give us the leading order behavior, okay? So because we're dealing with more dimensions now, we're not just looking at, a maximum like we would be for Laplace's method, or a stationary point along a stationary phase along one direction, right? We have to concern ourselves with these properties that we want satisfied along both directions, which are essentially where we're going to find a saddle point, okay? So a local analysis of saddle points, okay, then is going to give the leading order behavior, okay? So there's a little more work up front in identifying these saddle points, which we'll talk through in some examples, okay? Now the full asymptotic series expansion is going to require a non-local analysis, okay, from our deformation points, or deformation process, and then our endpoints of our integral, etc. Okay. Another way to think of this is that the main question of the steepest descent method is how best to deform some contour to exploit Watson's lemma, okay? So remember way back at the beginning of asymptotics of integrals, this is one of the first principles that we used in order to approximate Laplace type integrals, okay? And here we're operating in a complex plane. And so we're saying we want to essentially be able to use Watson's lemma that, that provides us with something like a Laplace's method approximation if we look in one direction, okay? All right, so I know this is a lot of background. I'm going to work through, I think, 2 or 3 examples now to kind of close out this method, and hopefully that starts to cinch some of these ideas together, okay? So to start, yeah.
Sorry. In the integral on the top, how do you end up with the t outside of the integral?
Yeah, so because along this contour, this is constant.
Oh, okay. Okay.
So the imaginary part of your function rho, if you separate things out like that, you choose it specifically so that this imaginary part is constant, and then you can pull it out.
Got it.
All right. Okay. So let's pick an integral that we've already done before. So we already know the answer, but we're going to look at how to deform this contour, how to deform a contour integral in order to compute this using steepest descent. Okay. So we're going to return to this integral that we've looked at in some form before, okay, as x goes to infinity, okay? Now, what's our general approach in this case? So now let's sort of walk through these steps in a specific example. We want to start by identifying the critical points of the integrand, okay? So what are they? Well, there's saddle points, there's endpoints, there's singular points, okay? Secondly, you want to find the paths of steepest descent. And let's call these CS here. And in order to do this, it's sufficient to know kind of the qualitative features of your integrand in this case. Right. Third, we then want to deform C onto CS. Fourth, we're going to use Laplace's method. Okay. All right, so let's jump in. Our particular value of rho is going to be IT squared, right? And then we have that asymptotically large value of x. The derivative of this with respect to t is 2it0, and it's equal to 0 when t0 equals 0, okay? So that's our critical point. And that is going to be a saddle in the complex plane. Okay. So d2 rho dt squared evaluated at t0 is going to equal 2i. I'm going to write that out in terms of complex exponentials, 2e to the I pi over 2 is not equal to 0. Okay. So we want to choose CS now so that the imaginary part of rho is equal to the imaginary part of rho evaluated at t0, which is going to be 0. Okay. So we want to be able to take that imaginary part and choose a contour that's going to keep that value constant. Okay. The imaginary part of I t squared is going to be equal to the imaginary part of I. And I remember, even though t is evaluated along the real line here, okay, or from minus a to a, which is just reals, we're going to deform this contour, this integral into a contour integral in the complex plane. So we have to consider the possibility that t is complex value. So then t can be u plus I v squared. And this is going to be equal to, its imaginary part is just going to be I squared, u squared minus v squared. Okay. And we want to look for where that's equal to 0. Okay. So those are going to be sections, or level curves through our complex plane, if you like, along which the imaginary part of the argument of the exponential is equal to a constant value. And that constant value needs to be the imaginary part at our saddle point there. Okay. So if we cut these contours in this way, then we can exploit these, sort of steepest descent curves. Okay. So along these curves, right, the imaginary part of I t squared is equal to 0. Okay. So we can draw this out, and then we see essentially how we sort of cut through with these contours in order to exploit steepest descent or the saddle point. So let me draw this now. So oops, that around. Okay. All right. So now if I look at U and V here, the UV plane, these are the two curves that I get, right? So I get U equals V and U equals minus V, okay? And we can do a local analysis to find our steepest descent directions, right? Now, in the general case, if dm rho dt m is equal to 0 for like m equals 1, 2, 3, up to some n minus 1, okay, then rho of t minus rho of t0 is going to be asymptotically given by t minus t0 to the n over n factorial, right? The typical Taylor series approximation. T equals t0 here, right? We let the n rho dtn t0 is equal to a e to the I alpha, and we let t minus t0 equal r e to the I rho, then rho t minus rho t0 is then approximately equal to r to the n e to the in theta divided by n factorial a e I alpha, which is equal to r n to the n over n factorial cosine of alpha plus n theta plus I sine alpha plus n theta. Okay. So sine of alpha plus n theta is equal to 0, and cosine of alpha plus n theta is less than 0. Okay. And so these are going to be our steepest descent directions. Okay. So in this case, for n equals 2, our descent directions are going to be where theta is equal to minus alpha over 2 plus pi over 2 minus alpha over 2 plus 3 pi over 2. Our ascent directions are going to be where theta equals minus alpha over 2 minus alpha over 2 plus pi. Okay. So for our example, d2 rho dt squared of 0 is equal to 2e to the I pi over 2. So that means that our descent directions are going to be minus pi over 4 plus pi over 2, which is equal to pi over 4, and minus pi over 2 plus 3 pi over 2, sorry, minus pi over 4 plus 3 pi over 2, which is going to be 5 pi over 4. Okay. So in the, this is the pi over 4 direction. This is my 5 pi over 4 direction. Okay. So this is going to be our steepest descent direction for this particular problem, right? So that means we want to draw our contour, C prime, along this line here. So the idea is that we're going to add some contour here. We're going to have to construct some contour integral now that includes that deformed contour. Okay. So, so we're going to have our steepest descent contour. We're going to have our original contour. And then we're going to have some sort of deformation contours that connect them. And that's going to make for us a contour integral that we can then compute in order to get our integral. Okay. So now we're going to deform C to our steepest descent contour, C prime. And we're going to get a union of our descent paths and our deformation contours, okay, along which our imaginary part is going to be this constant value. Okay, let me just sort of draw this. So here's now going to be our steepest descent path. I'm going to call this C1. We'll call this C2. And then we have minus A and A here. We have U, which is the real part of T. And then we have V, which is our imaginary part of T in this case. And this is our T0 point here. Okay. So what do we get? Well, the integral along C1, e to the I t squared dt is going to be the integral from 0 to epsilon of e to the ix ir squared times e to the I pi over 4 dr. Okay. So what have we done? Well, along C1, we've used that IT is equal to R e to the I pi over 4, right? So for R greater than 0. So we can parameterize along C1 using this ray represented by some radius times e to the I pi over 4. Okay, so that's going to give us a curve along our one steepest descent direction. That change of variables is going to give us dt equals I e to the I pi over 4 dr e squared equals IR squared in this case. Okay. All right. So then our integral C1 e to the I x e squared dt, okay, is going to be approximated by e to the minus e to the plus I pi over 4 integral from 0 to epsilon e to the minus x r squared dr, or e to the I pi over 4. I can just extend that integral all the way out to positive infinity because of the rapid fall off in that direction. And evaluating that integral by a change of variables, I can get that it's 1/2 square root of pi over x e to the I pi over 4. Okay. All right. So we're at time now. We still have a little bit of work to do left with this problem. But let me sum up what's happened so far. Okay. So our general approach, right, was to identify the original critical points of this integral. We identified the one that we had essentially as at the origin. And then in order to identify the paths of steepest descent, we first of all found where the imaginary parts of our function rho was going to be constant, okay? And then in order to specifically select which of those is the path of steepest descent or steepest ascent, okay, we needed to choose particular values of n for our, we needed to choose particular values of n associated with quadratic approximation in our case, and in particular where we would expect the second order derivatives to be the first order derivatives to be falling off in those directions. Okay, so that gave us our steepest descent directions. We chose contours that lived along those steepest descent contours. And then we're just now computing the value of those integrals, okay? The next steps would be to find the way to deform the rest of our contour so that we could get a closed contour, essentially exploit the residue theorem, or just Cauchy's theorem for integrals around closed contours, okay? And then use that matching equality in order to find the integral along our original contour, okay? All right, so Are there any questions about this so far? Because I think this is probably the method with the most moving parts of all the ones that we've covered. All right. So, so my plan then is to finish up this example on Monday and do 2 more examples to really try and nail these points down. And then you'll have a chance to practice method of steepest descent on homework 3. And then we'll be essentially done with well, introducing new methods for asymptotic approximation of integrals, and we'll move on to ODEs probably middle of next week. Okay, and you'll have a couple practice problems on that on your homework. Okay, all right. There's no more general questions. Have a good weekend, and I'll see you all on Monday.
Thanks, Zach.
Thanks.
Thank you. I was wondering about the project, if and sort of what I could do. I don't know if you have time to talk about it now. I can always come to.
Yeah, that's fine. Yeah, no, we can chat now if you want. I'll just turn off the recording.